Hello everyone, my name is Liu Rui. I'm a research fellow from National University of Singapore and the Singapore University of Technology and Design. I will make a presentation about our paper on TTS, GraphSpeech, Syntax-Aware Graph Attention Network for Neural Speech Synthesis. It's based on paper 5299. This presentation includes the introduction, baseline Transformer-TTS, purpose method GraphSpeech, experiments, and the conclusion. First of all, I will come to the first section. Text-to-speech seeks to synthesize human-like natural sounding voice for input text. With the advent of deep learning, end-to-end TTS models simplify the synthesis pipeline with an encoder-decoder network. Transformer-TTS is one of such successful implementations. Transformer-TTS adopts self-attention mechanism to achieve parallel computation and model the long-distance context of the input text. However, the self-attention mechanism in Transformer-TTS doesn't model the complex syntactic dependency of words with a sentence. Graphical structure plays an important role in natural language processing, and it often serves as the central formalizer for representing syntax, semantics, and knowledge. Inspired by this, we propose GraphSpeech to encode the syntactic knowledge. Next, I would like to revisit the Transformer-TTS framework. Transformer-TTS is a neural speech TTS model based on self-attention network with an encoder-decoder architecture. Given an input token sequence xy to xn, the attention score between the token xi and the token xj is simple the dot product of their query vector and the key vector, like this equation. While self-attention-based encoder builds the long-range dependency between any two tokens to model the global context, it doesn't model the complex syntactic relation of words with a sentence. Many works validate that syntactic information is very useful in speaking style and prosody modeling. To address this problem, we propose a novel model, GraphSpeech, to encode the syntactic relation of input lexicon tokens in a sentence, and incorporate such information to derive syntactically motivated character embeddings for TTS attention mechanism. This section looks at our proposed method. Our work provides the following contributions. We propose a novel neural TTS architecture, GraphSpeech. We formulate the extension from syntax tree to syntax graph and character-level relation encoding. We propose a syntax-aware graph attention mechanism which incorporates linguistic knowledge into the attention calculation. And GraphSpeech outperforms the state-of-the-art Transformer-TTS in both spatial and prosody modeling. To our best knowledge, this is the first implementation of syntactically informed attention mechanism with a graph neural network perspective in Transformer-TTS. As shown in this figure, the proposed GraphSpeech include a relation encoder, graph encoder, and the decoder. The relation encoder extracts the syntax tree from the input text, then transforms the syntax tree into a graph structure, and encodes the relationship between any two tokens in the graph. The graph encoder presents the syntax-aware graph attention mechanism, which not only focuses on tokens, but also their relation, thus benefit from the syntactic knowledge. The decoder was used to predict the acoustic features frame by frame. Next, we will explain the relation encoder first. Relation encoder converts syntax tree of input text into a syntax graph that describes a global relationship among the involved input tokens. As shown in this figure, in a syntactic dependency parse tree, only words that are directly related in a sentence are connected. Others have no direct connection. To learn syntactic relation between two words in a sentence, we hope to extend the topological structure of the syntax tree to build fully connected communication. Like the original arrows in this figure, we change the one-way connection into a two-way connection by adding reverse connection. Moreover, we introduce self-loop edge with a specific label for each word. Self-loop connections are omitted due to space limitation. With the two-way connections as in this figure, a word is able to directly receive and send information to any other words, whether they are directly connected or not. Now the question is how to model the relations between two nodes. We note that the relation between a node pair is depicted as the shortest relation path between them. The shortest relation path SP between the node I and the node J denoted as this equation, where function E indicates the edge label and ky to kn are the relay nodes. We employ recovered neural networks with bidirectional GRU for path sequence encoding. The last hidden states of the forward GRU network and the backward GRU networks are concatenated to form the final relation encoding Rij. The final relation encoding represents the linguistic relation between two words. In neural TTS, the basic unit in a sentence is character token. We extend the word-level relation encoding to character-level encoding here. If two characters belong to the same word, we use self-loop edge encoding RII to define their relation encoding. If two characters belong to different words, we directly use the relation encoding Rij of the word they belong to assign their relation encoding. Next, we will discuss the proposed graph encoder. The graph encoder incorporates explicit relationship between two nodes into the attention calculation, denoted as syntax-aware graph attention. As shown in this figure, multiple blocks of syntax-aware graph attention and the feed-forward layer are stacked to compute the final character representations. And each block, a character embeddings is updated based on all other character embeddings and the corresponding relation encodings. Relation encodings derived from relation encoder only encodes the shortest path between two characters. To encode the direction of the connections when calculating attention, we first separate the relation encoding Rij into the forward relation encoding Ri to G and the backward relation encoding Rj to I. Then, a syntax-aware graph attention was used to compute the attention score, which is based on both the character representations and their bidirectional relation representation. Term A captures purely context-based addressing, which is consistent with Transformer-TTS. Term B represents a forward relation bias. Term C encodes a backward relation bias. And term D encodes the universal relation bias. With the syntax-aware graph attention, the syntax knowledge was used to guide the character encoding by incorporating explicit syntactic relation constraints into attention mechanism. Lastly, the syntactically motivated character embeddings are taken by the decoder for acoustic feature prediction. The decoder follows the same structure reported in Transformer-TTS. We use mere linear, postnet, and stop linear to predict the mere spectral and the stop token respectively. In this way, the decoder learns to associate input text and its syntax with output contours. Now we will move on to experiment part. We conduct objective and subjective evaluations on LG speech database. We use Syndanza to extract the syntactic dependency parse tree. In all experiments, we use GraphLim algorithm for waveform generation. We list the model configurations and here. We use the state-of-the-art Transformer-TTS as the baseline. First of all, we employ MCD and RMSE as the objective evaluation metrics. It's observed that the proposed GraphSpeech provides lower MCD and RMSE values that validate its effectiveness. We then evaluate Transformer-TTS, GraphSpeech, and ground truth in terms of mean opinion score. As shown in this figure, GraphSpeech outperforms Transformer-TTS by a large margin and achieves comparable results to that of ground truth speech. We further conduct A/B preference tests. It's observed that the proposed GraphSpeech model outperforms the Transformer-TTS consistently and close to natural speech. You can access this link or scan this QR code to enjoy our synthesis speech samples. Finally, we conclude this paper. In this work, we propose a novel neural TTS architecture, GraphSpeech. The proposed syntax-aware graph attention mechanism effectively models the linguistic relation between any two characters of the input text. Experiment results show that GraphSpeech outperforms original self-attention systems in both objective and subjective evaluations. Thank you all very much for attending these presentations.